All right. Let's see if we are live. Hello, everyone. Welcome to the stream. Today we are going to solve a reverse engineering challenge, and I have not looked at this challenge before. It's created by my friend Lars, and it was originally used for. They had like a speed-pwning, speed reversing tournament at the Midnight Sun CTF. Kind of like I think it was like a separate side event thing they did, and this was one of the challenges that he had created for this. So I think the idea is that this should be fairly quick to solve. So we'll see how fast I can do it. By the way, if there is everything fine with sound, video, so on? I see some comments in the chat. So yeah, looks good. Okay. As I said, I have not looked at this challenge before. I've just started up my virtual machine here. We have this packed archive with the challenge. And let's actually try to, we can time this. I don't know if Lars still has the times for the person who solved this at the tournament, but we can see if we can beat that. So I have this thing that will 2.5 hours was the fastest. Okay, so we do have some time. That's not speed reversing. Okay. Anyway, so I have this command here which will update the status on the bottom, and it also logs the timestamp of this. So if I also do the same thing when I finish the challenge, we will be able to see how long I took. Also, it's live streamed and recorded, so you will know it from that. Actually, can I just check? So is this like a normal CTF challenge where you're supposed to get the flag somewhere in the, or is there like some different kind of setup because of the tournament setup? If I can just get a confirmation from Lars. Normal setup. Okay, cool. I think that's enough of me talking. I will try to keep an eye on the chat a little bit. I have it here on my other monitor, but I will try to take this seriously, and I will try to be fast with this. So I will probably not have time to like go on like long detours to explain things. So this will be maybe less educational than some of my normal streams. So I want to see what how I can handle this. If I can handle this challenge and like solve it quickly, and I want to give it an honest attempt. Okay, enough talking. When I press enter, we go. So yeah, that's good. Lars will take some detours in the chat for those who are interested. So Lars in chat, the person who made the challenge. Okay, with that, let's go. 3, 2, 1, go. So we will unpack this. We have some binary, 64-bit elf. We have some notes.txt, info diff must be func. Okay, cool. I don't know what that means. Question about timer. I don't really have a timer, but I have the timestamps for when I started and ended. I don't have an on-screen timer, but I started like 7 minutes past, so you can figure it out. I was thinking about setting up a timer, but I didn't really have time to do that. But I have, when I changed the status of the stream, it logged the timestamp of this. So if this is another VM thing, I'm gonna be a bit sad. Okay, this is a bit weird. Oh, it was a subscriber. Thank you. Oh, I still have this thing going on. the notifications. So doesn't seem, just going through all the functions, trying to see what's going on. I mean, there's not a lot of code. Here is something that's like, could be, I see. This is some really messy stuff going on here. Okay, we can see we have only a very small piece of code here that's actually identified as code. And then there's some of this. Okay, here we have, this looks like, yeah, so this is like a big banner thing. Where is this referenced? We don't know. Oh, actually, it starts up here. Here's a new line here. Okay. So this is like a big, some kind of like ANSI art string thing. Yeah, exactly. It will print this whole thing, so we don't really need to care about that. That's, I mean, maybe some banner or whatever. So this is not very interesting. We have the win string. This is going to sound like some kind of excuse, but my mouse is starting to break down. It starts to like, it started to double click and sometimes not click at all. So this is why if you see me suddenly navigate to something I shouldn't, so I need to buy a new mouse. Bunch of function pointers all over the place. Okay. It's not a lot of stuff overall. This is a stack cookie though. Soon you will either love or hate me. Well, I already hate you, Lars. So it's that's all good. Depending, the only question is, will it be better or worse? Okay, this is like the result string. So this is kind of the check function. So this is like, I don't know, some kind of check. Because like it starts with a nope and then it checks for a win. So do we have imports? Not a lot of stuff. There's the puts, there's malloc. Oof. Yeah, that's not a lot. This is, what's this? Some mallocs. BTS. Okay. Of course, Lars is using some kind of weird instructions. Larger font. Yes, we can do that. Font size 18, maybe. Yes. Thanks for reminding me. x86 bit test and set. Oh no. Okay. What is this? So we have some kind of loop going on here. Calling, wait, are we calling malloc in a loop? XOR. All right. Okay. Not entirely sure what this function is doing. I mean, I would expect some kind of do we give it as a command line? Okay. First we gotta name these things properly. This is the argv. This is the np. Okay, so this is down here. Okay, right. So this is the arg1. Okay. So I guess we're supplying the flag through as a command line argument. And then v4, and then it's v12. So okay, we're setting up some kind of structure here, and then we're setting the address there, and then we're passing this in as an argument to the check. And what's this? Offset to, okay, this is probably a lambda, NAND. Oh, NAND not. Okay. Is it a like logic circuit thing? If, and then just an A or sub. Okay, it's some kind of VM, maybe? Fold, helper, lol, what the fuck? Okay, yeah, that's a normal instruction. See if, okay. So is this like instruction set thing going on here? What's this? Where are these used? Huh. Is this like a tree structure? Not lambda. Is this like a whole like AST that's been like compiled down into like a tree structure and embedded um, into the code? I mean, maybe. There was a question if I ran strings yet. No, we can do that. But yeah, massage. Okay. Yeah, there was nothing more here. Okay, cool. We can try to run the program as well. Speed 5. Yeah, okay. That was just uh, the banner. Pretty cool, by the way. So I suspect, or I mean, I don't know, but, and then this is some kind of recursive thing going on here. And these all seem to be unused. Let's get rid of that. Looks better. So we call this some kind of like unknown tree. Oh no, we cannot have that prefix. Okay, just call it tree, actually, global. And this is our input structure. So we have this tree thing. I mean, potentially a tree thing here. So what's this? Like, does this make sense? Like, this would be a not operation, and like which is a operation with a single operand, and then this would be the pointer to that. So what's this? This is an OR, yes. This points. No, wait, okay. Mm -mm. Yeah, we'll see. We'll go back to the code again. Actually, let's try to create this structure here that we're building up. This V9 though, I'm not sure what this is, because this is not part of this is further down the stack. It doesn't make sense that this would V8. Okay, maybe that's a structure in by itself then. Okay. We call this just struct1 and struct2 for the time being. I don't really know what they are. Both of them consist of 2 keywords. We go back here. We call this a struct1, and then we call this a struct2. Set the type. Yes. Looks reasonable. And this is like, we can call this like input struct. I mean, it doesn't quite make sense, but it makes less nonsense. I don't know. There's this thing going on with these like kind of strings, and you have this hex 80 thing at the end. But so if this is a string then, which we know it is, this is like some argument. So this is kind of like the current pointer. Oh, so we're kind of converting this. We're stepping through this, and we're converting this into this other. Yeah, here we have this thing again. So there is some kind of these like elements in this like structure, this tree, this chain, whatever it is, and we're kind of like converting a regular string into this format. And we are setting this as, so what is this? This is bring up Python. Verify, right. So I'm starting to believe this kind of like AST thing. So basically, or some kind of code basically. So you would have like the name of the operation somehow, and then kind of like the operand, and this is kind of is then maybe some kind of string type, and then we run this through here, something like this, or matching against it. It's I'm not entirely happy with this explanation quite yet, but it's like something in this direction, and this is quote. They're backwards because it's like little endian. So these are strings, not really numbers. Same thing here. Lambda again, right? Save this. But okay. So this is shifting down to get those this high thing here in each operation. And then why is this? I don't think this is correct. Or is this? I don't know. That looks weird. Why is it comparing against a function pointer? What address is this? Yeah. Okay, a bit. I'm not sure about that. What's this? Unclear. We probably should go into some dynamic analysis fairly soon, but we know that I always hate that. But let's go with this idea of this being some kind of tree structure. So let's just call this like op1. Maybe there are like multiple different structures. Please solve it without dynamic analysis. Okay. This is just taunting me now. So this is shifting down. No, wait, this is not. What? Okay. It's not dereferencing the pointer. It's looking at the low. I mean, here we're taking the address of this and then looking at the like top 2 bits of that. Is this just checking where, like, whether this is on the stack? I don't know. And if it's less, if this is less than, then we return. Yeah, that makes no sense. I'm gonna check the disassembly that we're not getting tricked. No, this looks reasonable, I think. Not terrible. Um, There was another string I didn't look at. Oh, okay. I should do this in my head. If. Okay, yes, that makes sense. Um, what function is this then? Okay. Yeah. Feel we need to start looking into this. I mean, this somehow we can call like operation name or something. I mean, I'm not super happy with that, but uh, it's something along those lines. It's not really in the name because we have these like top bit part where there's something strange going on. This is the tree argument thing. So let's say, so here we get into this name thing where it checks whether this thing matches. If these match, then we. So is this kind of like, if this was also like an op1 pointer, this is in if the top 2 bits are set. There's something about these top 2 bits. Can we go back to this tree thing again? Here. Can we find an example where it's not 80? Verify. Sub hash. Maybe what if we just parse this? Oh, here's a one which is different. That's cool. What if we just parse this whole tree and just visualize it? Maybe that just will tell us something, but we need to kind of figure out what the structure looks like. So we have, it starts here, right? So this is the start of some node in this thing. And since this is pointing to here, then we can probably guess that like it doesn't have like an internal pointer. So this should be one structure of 2 elements. And then we have another structure here. And like by the same reasoning, this is like a 2-element structure. And then this is that what we get from the, does the name say whether this is like a binary or this like top bits here. Maybe it says if it's like a binary or unary operation. Hmm. Maybe not. No, but that doesn't make sense because both like not should be a like a unary and NAND should be a binary operation. So that's not what the flags indicate. Uh, I feel that we are going to want to parse this whole thing, like regardless of where we end up, we are going to so sometimes maybe it's not sequential, maybe it's yeah, maybe yeah, there are pointers here internally. It's just like I mean, this is some kind of big data structure that has been like packed and stored in this binary. So you see they all have pointers to each other, and of course initially they happen to be next to each other because uh, but they should start drift. Maybe not. Like what happens if you go down here? Are they just Is it just one big chain? Uh, no, here, for example, you can see this structure that starts here. It's like pointed to by this thing, and then look, here we have and this is so we have maybe something that's like an if, and then it points to A, which points to C and B, and then this thing points down here. We don't know what that is. And then this is just 0. Uh, yeah. So these are kind of the leaf nodes of this, maybe. Like, where is this thing linked? Up here somewhere. Here's a cons. Yeah. So we probably need to parse this. Okay. How? So we need. Oh, wait. Here is. What's this data? Uh, oh, no, this is okay. Not what we're interested in. Okay. So how do we know? How would we do this properly? Oh, here's also a large jump. Um, so does every does every one of these actually just have like is it always two children? Is this like a binary tree? Maybe that could make sense. Okay, let's try that. Okay, we start here. No, sorry. Do we? We start exactly. How is this stored in the this would be the virtual addresses, I guess. Can we do this from the Pwn Tools elf library? Okay, so let's start writing some code. Mm, uh, Increase the font size a bit. Hello. Um, so be called, so we call this, what's it called? Speed rev 5. And then this is the tree root is at this thing, and then bring up the pwn tools. Elf read. I think we can use this to easily just read based on the virtual addresses. Let's see if this makes sense. Because what's actually stored here, it's going to be 5370, which actually, and then here. Okay, that's cool. So, right, no, we want to read. There was the read here. Unpacks, and yes, this is exactly what we want. So, for example, if we do binary U64 tree root, and we can just we just try this. Yes, excellent. Okay, so we need to be careful here if because some of these are offsets and some of these are these instruction things. Oh, and that's why we can read this. Oh, so that's kind of like an indicator. Okay. So this is a node. And then for each node, we want to read the this is kind of like if this is like a binary tree, this is like left and right of the tree, and then we want to read this. So this would be something node left, right. That does make sense. We get this one, which points to this and this. And then we need to recurse. Okay, so, okay, for now, I'm just gonna print stuff out. Later, we can think about like building up like like a data structure or whatever. So let's do if left, and then we do the 62 thing. If this is not equal to 0, no, sorry, if this is equal to 0, then we can do parse node left, whoa, and then we do the same thing with right. It should actually maybe actually call the function. How about that? Recursion depth, that's a problem. Another problem is, hold on, what? Going to address 70 should give us 5380, 5420, which should be these two. And, oh, right, yes, here, this should be node offset, not node. Thank you. Okay, this is cool. Address this is not contained in ELF. Makes sense. Wait, why does this go? Okay, hold on. Oh, okay, there's also the 0. No, wait. Right? Oh, yeah, okay. We should also check that it's not 0, because that's also a thing. Yes. Oh, maybe this is like going to be like assignment stuff or something. So let's do and left is not 0 and right is not 0. Let's see if this is enough. And now we got this thing. It's not contained. I mean, we kind of see we are building, we are kind of traversing through this thing somehow. A little bit unsure exactly what's happening. Okay, let's see. Where did this come from? 2309. That's interesting. So here is like a case we haven't seen. Like, how would we handle this? Oh, this goes to like an actual function that does something. Oh, and that's why it's looking for the comparison to the offset. Look, this is basically saying like if the operand is like less than this, then because it might be like an offset, like an actual function thing. Can we get binary symbols? Can I do this? Is this not? Ah, it has a dot in the name, of course. No. What's like is it this translated to like an underscore or something in this symbols table? Okay, can we just print the whole thing? Uh, no, is it in like exports? Is that a separate one? Symbols. Otherwise, we'll just look up the. Okay, whatever. Let's just. I mean, it should be in exports, but it's not. Uh, Functions. Okay, let's not waste time. Let's just take this offset. Let's do this. So these can be combined. Okay, and now we have parsed something. And here we can see these things which are possibly like strings that have the 80 thing. So we can do, let's try to, uh, we should have a case for this and like print this nicely. Because there was some of these like 80, 80, 80. Here's like 40. So this could be like a different category of operations. Like maybe some of these are like functions or operations. Maybe some of them are variables, and so on. Later, we might actually render like an actual visualization. Oh, yeah, I can never pronounce that word. Visualization. So let's do let's do and then we do if left equals 2, then we do um, and in that case, we're going to do something, and otherwise we will print the hex value and just keep the value as is. Just going to make a function out of this. Um, so I'm just like making it nice when it prints these out. Maybe actually use the value here. Okay, excellent. And then we do the formatting here, which is to, we want to take the operand, we want to AND it with like the opposite of this, and then actually we can just then do, yeah, but yeah, we can do that, Lars, but we can also just not do that and do a operand, we pack it, we drop the last byte, and then we do a strip to get rid of the null bytes. And then we should have, oh, wait, what? Oh, the default is not that. So this, and then finally we decode it as a string. Nice. Um, okay. Now we are getting somewhere, I think. Uh, we have these offset. Yes, this is right. Don't give me too many hints though. This is only if I'm stumbling around for too long. Okay, now we can see that the 40s are still here, and they or the ones with 4 as the top thing. No hints, just pointing out your mistakes. Well, I mean, yeah, I guess. Uh, right. So we should look into some of these low value functions. Yeah, okay. So these are kind of like some implementations of like some operations, I guess. Uh, maybe it's time to actually just generate. Like this is not huge. Like this is like a moderately sized tree. Maybe we should try to actually generate like a graph of this. So how would we want to do that? Um, mm, we where do we log this? Okay. Uh, we temporarily let's save both the left and right thing. Um, and then comment out this, and then we do print, and we do operand. No, that's not the name. Node offset arrow to um, um, maybe we should already just do the formatting inside of here and skip the fragments. Just do this, and here we do operand. Yeah, let's do this and not be complicated. And then when we log this, we already have it like this. Let's just see that I didn't break anything. Okay, cool. Then we can get rid of this and go back to this and do left format like this, and then the right format. So now we're just splitting this up into multiple things. Yes, but this should be this. Yes, and then add a semicolon like this. Um, you need to get rid of this log statement, graph one dot dot. we have, okay, get rid of that. Digraph, program. This, okay, this is going to be terrible because all the zeros are going to point to the same node. But let's just try this to start with. Badly, can I not use this as names for my examples? No, not the. Okay, maybe I cannot use that as a name. And we do like, just put like a letter in front or something. Oh, okay, we have something. Yeah, amazing. Um, yeah, this is only mildly helpful right now, but it is something. These are probably some kind of constants that we are. I mean, this is probably going to be some kind of like hash function or something, and you can see that these values here, they kind of stick out. But yes, we need to probably separate. Okay. So we need to be a little bit more. If I can zoom in, yeah, I mean, I can zoom in, but it's not very helpful. So we're gonna start being a little bit more clever. We're gonna start actually giving each node a unique name and then give them labels and stuff instead. So let's start by like separating the generation of the tree separated from the presentation of it. So we do um, and then we have the offset for the node. Uh, so basically, when we get one of these, node is, we always create a node based on the offset. And then if we do a recursive parsing, we assign that to the left thing. Otherwise, we assign just the value itself to that arm. Do this, and then we return the node, and then we have like the root like this, and now first we just need to have get all the nodes into a list, which is easy. We create a, or like all the let's see, we want all the offsets. So we recurse into both sides. So let's, no, run this. Oh, we don't, wait, what? We always, we should always be setting it to something, right? Self-right list nodes. Non-object is not, how would that? I mean, one of these two branches will always be taken. Um, let's see. Oh, you actually need to return the result. That's a good idea. Okay, great. So these are all the nodes in the graph. That's great. So then you can do you can do for node in this. We can print the node. No, this is just the, well, this is just going to be the off. which is not, let's get the actual node, and then you get the offset like this. Yes, yes. And then you can do label equals node offset hexadecimal, semicolon at the end. Need to close the thing. Yes. Um, uh, we should get the others, actually, we should wrap the other ones in. Just make a leaf node here. Because then we can start making separate things with that. So let's just do this. Because then we can separate these things, and then we do here we can then also save the leaves. Uh, so we get the. So I'm just kind of like just traversing the graph here just to get some lists and stuff with all the different parts of the tree so that we can then format them into this GraphVis format. Um, so that we can easily so that we can easily visualize this. Yes, this is. No, wait. Now we have nodes in here as well. Why? Easily visual. Yeah. This is definitely. This is because this is incorrect. Uh, leaf. Yes, please. And then because then we can number these. So we can do leaf number. And now we can do. We can call this. Let's call this leaf number, which we add to, and then the label is just the value like this. I mean, this, and actually maybe use the right variable name. This is excellent. So now we can go back to the leaf and give it an ID, which we can give back, go back here, and then This is excellent because now we can do we can create all the edges. So all the edges we can then create. So the starting node is the node of that thing, and it goes to. So here we need to do if node dot left is instance. This is pretty dirty Python code, but anyway. So if the left one is another node, then we do node left because the offset is the identifier, and otherwise we do the ID as the identifier. And of course, we need a semicolon at the end of each of these lines. And here we need to change everything that's left to a right. And now we have a lot of stuff, except we should do the whole thing like this, so we don't forget to, yes, please. And then now we just wrap this in a diagraph program. And then at the end, we need a closing bracket. So this should be a valid dot file. And then we run dot on this. And I should just do this directly from the Python script. And so I don't have to be careful about the output. We go back here. We go back to here. Much better. I think. Except this is weird. There should only be 2 outgoing edges from each thing. And I mean, we're getting somewhere. We are getting somewhere. We should do some formatting on some of these. We have these big values, which are all of these string operations, maybe? Or I mean, the strings. So actually, we could do that. We can do that in here. Hello, SPQ. So we can do if value is less than the term proc offset. Then the label is function and then the value and then a hex thing. Otherwise, if the value is less than this, then actually no. Let's do this down. It's not 0. Then we do, that was our condition. It was if specifically if it's 2. So again here, if this is specifically 2, then we set the label to the string thing. And then otherwise we do just set the value to the hex value for now, but we need to we need to consider the we should consider that other four thing. And now dot graph. Let's actually replace these prints with this and oh no, the new line, and then just do we write this to the file. Maybe actually use the correct thing. Convert this. Oh, kind of nice. Kind of nice, except, oh, yes, we need to take care of that. The 0 is not, so that's another label thing. Here, if value is 0, let's just do 0. Okay, starting to look kind of fine. Uh, uh, think we still have this weirdness. Why does this have multiple outgoing? Why do these have? Oh, okay. Maybe it's because it's compressed. So these, like for every ingoing pair, we get a repeated. Okay, so we might have to deal with that. Maybe. So this is kind of the tree that's embedded in the program. And crystal clear, in my opinion. Yeah, a bit unclear how Lars dared to call this a speed reversing challenge, but sure. It's interesting with all of these lambda. Actually, we should go back because we had that was like a special case in the program thing, right? We had the if the quote and the lambda, they are handled like in a special way. Um, so this is not really, let's go do some more reversing here. This is like left and right, is basically what we can call them. And this is just like a node something. Uh, this is this current node. This is this tree, which is also a node pointer. So let's check here. Basically, if while the main node does not have the top bits set, okay, it makes sense, I think. Then we check, like, if this is a low value, then we just return a pointer to the left, wait, uh, I mean, this is just, isn't this just saying, isn't this just the same as saying, wait, the same as returning itself. This is just a weird way that IDA displays this portion of this thing. Yeah, exactly. So the left is offset 0, exactly. So this is just the address of the node. Where was this recursive call? Here. So how is the, okay, so we do return like a value. Is this the only place we recurse into this? No, it's inside here as well. And this is called from the, okay. That's this thing. So if, let's see, if the operation is quote, then we return the right side. Otherwise, if it's exactly 2, we get, so this should not be called, this should be left. Or maybe like result or something. Here we call backseat reversing. A very minor amount of like to correct like stupid mistakes is allowed. So here is the case where the left function is a function pointer. So in those and in that case we call it again with 2 arguments, and this is, so they are all called with this thing. And so let's fix these up again. This is a node. And that, we allocate a new node. Okay, right, that makes sense. This is like the new node. So this, and that would make sense, right? If you're processing like an instruction tree like this, you would start at like the leaves, you would like process that subtree, and you would replace the result of that subtree with the result, like a node containing the result. So maybe that's what's going on here. So this is just this is never assigned to, so we can do, no, actually. Right, so if the left this argument exists, or like if it's not null, then we allocate a new node, and then we take the current right-hand side of the node, and then we assign this to the new right-hand side after being processed inside here, while the left one is just copied. No, this is here. So this is like going left. This is basically recursing. I mean, in some sense, like traversing down the tree, getting the result here. We call this function. Here, if the left-hand side is in this like function range, but So Lars is sending encrypted messages to the audience. This is exit. So this happens if I mean, this should never, this first case here should equal to, okay, I mean, it could be if it's exactly equal to, which, yeah, or if this is not equal to lambda, then something went wrong, and then left here. Oh, this should also be a node pointer. Everything is node pointers. And then here we also start creating new nodes somehow based on the results maybe from, wait, where is 10 is, I mean, this is also a node pointer. This is also a node pointer. This is a node pointer. Yeah, it's node pointers all the way down. This is also a node pointer. So let's just call these like N1. This is, wait, okay, this we can just remap like this. This is N2. This can also just be remapped. And 3. So this is kind of reorganizing the tree somehow. Also some kind of tree operation. This is also a node pointer. And yeah, I mean, these should be mostly considered. Look, there's some going 2 steps down when we set the types correctly. Yes. No, this should be just like this. Starting to look kind of okay. This should also be taking a node pointer. I mean, of course, there will be some values as well, but I'm just going to make them all node pointers because that's what it's going to be in like the vast majority of cases. So we should probably look at these. First of all, can we just print all of these? So these are the functions that appear in the tree. So from like 2259 up until something. So it's like this one down to so 8 functions, 2259. This is the one. We can call this then like lambda 1, and then is it yes? A8 and CC. D7. E3. And 09 and 32, yes. So these seem to be the 8 functions that we can use from Yeah, and this is kind of like the convert input function, I think. And this thing is called from, oh, what's this? If the left is equal to something, then return. Okay. This is also some node operation. So these three here are kind of like our three um, transformations function. This is like the transform one or like parse or whatever you want to call it. Like the three functions that actually kind of operate on the and these other ones. Yeah, these are kind of like related to like startup and stuff. Okay, so we're kind of like mapping out stuff. And we know that we should have two arguments, right? Transform down here, we're calling it with two. So all of these we call with two node elements. So this should make the decompilation much cleaner. So we should be able to like just do this. Yes, this looks very much like a subtraction. And something else, but let's let's not get bogged down too much in detail. Maybe this is a multiplication. And this could be an and. And this is some kind of like the reference thing going on. And this is probably also going to be, so this is left, right, and left, left. And then we have a division here, I think. There's a bunch of masking and stuff going on as well, but I'm just gonna like disregard that for now and just assume that everything works kind of like as intended. And this is kind of like a comparison thing where you will return either one value or the other. Uh, and then this is, of course, a new node where we it's like duplicating the. Is this like a duplication? We take. No, wait. This is like shifting things around somehow. We're inserting a new node where the left-hand side is the current left, and then the right is the left of the right. Okay. Yeah, we're gonna have to think about that. Oh, I've been going on for like an hour and 20 now. It's pressure is increasing. We can look at the convert input thing now. Now that we know that everything is just nodes. This is N1, N2. Oh, here is some. This is quote. Okay. So here's a node. Let's call this N3 for a moment. This is the current value. And this is a flag if we are at the end of the string. This should be the current node, maybe. V8. Yeah, this is another new node. Okay, so we are making the input into this tree structure by taking oh, is this like some I think there was a cons as well. This is some like functional programming bullshit, essentially then. I'm pretty sure. Uh, so let's see, what is the thing we're returning? This is the result. So in the result string, we always assign quote on the left-hand side. And then on the right-hand side, we assign this node, which is like the then contents of the quote. Here, and then let's say we take here, we take the first value of the string, and let's see, we create a new current node. We create a new node here where we and this is like the next node. And then the left-hand side, we assign the value, and then the right-hand side, we assign the next node, which then becomes the current node. Okay, so we're gonna get this big chain of nodes. Wait, hold up. We reuse this pointer. Okay. So that's right. This is the first node in the chain, which we reassign here. I'm just going to assume that this message is also ROT13 encrypted and allow it, even though YouTube marks it as spam. Okay, so we're going to get this big chain of our input is going to look like what do you call it? Like a degenerate tree, where like you have to the left you have one character, and to the right you have the rest of the subtree, or the rest of the tree, except it starts with a quote. So this is like a quote. This is like a tree representation of a string. I mean, that makes sense. So that's fine. So then basically, in the main function here, we get, oh, what's this? This is going to be like verify then, I think. Verify, exactly. A lot of encrypted messages in my chat now. So this is like input 3 into this verify arg, basically. And then, so basically we have a tree where you have a left node that's verify and a right node that's another node, and that node itself has a right side that's a 0 and a left side that's our input. And then we send this as input into this like parsing thing, which then will have this tree, which is kind of like the program. And then we try to, and then it will traverse all this. Okay, so we kind of know what they're doing. Hello, Robin. Yeah, I kind of understand your kids. I'm not entirely sure what we're watching, but hopefully we're having some fun. Wait, where did all the function calls go here? No, here we have it. Okay. Um, hmm. Mm-mm-mm. So we just need to kind of figure out how to. First of all, we should probably sort these things out and not unify them into another to a node like this. But how do we? Or maybe we should have it like this, but we should not create the other nodes multiple times. Why are we doing this? Why do we have, why does this happen? If you look at this, for example, 5A80, 5A80. Oh yeah, this is referenced in multiple places, but mm, mm, uh, mm, mm, mm. So we need to kind of like deduplicate this. This node. Can we do just like I mean for node in node node dot offset is node, and then we do node equal nodes unique dot values. Can we just do this? Yeah, that's better. Now we have deduplicated everything, and we're starting to get something that kind of makes sense. Um, hmm. Mm-hmm. So this is no wait. We have a bunch of nodes here which are. Oh, is that because we get then the repeated wait leaves? Ah, shit. Then we need to collect. Okay. Yeah. Okay. This code we're just this like we're just discarding all of that work, and then we do leaves again. And then we just do for node in nodes. If node is instance, node left, and it's a leaf node, we just append that, and then we do the same thing for the right side. And this way, we should only have one of every leaf node. Yes, perfect. All right, 1.5 hours in, and we have a nice graph. We should now figure out what these things mean. I'm kind of guessing that they are like constants. That's my guess. So what does this mean? Let's see. While we have like a node of some kind, where do we have some shifts? Here, if if okay, so there's a specific case for this exact value for the if thing. Then otherwise, there's also a specific case for the quote thing. And then we shift down and get 2. That's the 80 case, right? Yes. Can I just do like B, and then it's because this should be 1, right? So in the case where it's 2, we do this. And then here it would do exit. That doesn't make left. I think I have the logic backwards somehow, but let's look at it. This is the case where there's like a function, like an operation to call. Then there's also this situation where we're doing some kind of rearrangement of the tree. Where does the while loop end, by the way? It ends here. And then it can also happen that we do like a final. I think this is kind of like a dereference. Here we take if the left. Still not exactly sure what this is doing. And what's the transform here? Let's think again what this is doing. If we have a node here, we create a new node, which is we transform both halves. With the left is just the left. Maybe speedgen refers to time it took to create it. Yeah, this is going to turn out to be just like compiled Haskell or something. Or fold. Oh, this is very annoying to read. B. So if we start looking at these, wait, 2259, was that Which one of them was that? 225. Oh, that was the sub, which is here. Okay, so is that just the implementation then? And then what's this? 227a, which is the multiplication, I think. Yes. Okay, so these are actually the names. And then you have car at 22cc. Uh, what's uh-huh. Car and CDR. Primitive operations on con cells, which is like a okay, so this Lisp con cell is composed of 2 pointers. Car operation extracts the first pointer. CDR operation extracts the second. Thus, the expression car cons xy evaluates x and CDR cons. Okay. Okay. I'm reading the Wikipedia article on car and CDR. So it's basically just get the left and right pointers. So 22cc would be car, and 22d7, could that be CDR? Yes. CDR. And the only one we don't really know about is 2332. Yeah, that's cons, which is like to put two values together into a list, I think. If I remember my functional programming correctly. Um, okay, so how do we kind of like digest this in a reasonable way? Pronounced Cudder. Cadder. Yeah. Yeah. And the car. Um, uh, and I'm just assuming that like all of these zeros is because this is like operations. We basically only have one kind of one relevant child in that node. Helper. Yeah. Mm. Here's something called hash. Um, hmm. Oh, we have Olle in the chat as well. This is a question where I can download this binary. So Lars shared it privately with me. I don't know if he wants to publish it or anything, but yeah, that's up to him. Um, how are these things referenced? I assume that we're somehow binding, because these function addresses, they seem to only show up in like a single place here. So it feels like we're somehow defining these, like binding these function implementations uh, to these names, and then somehow we can refer to it. For example, here we have the div thing. So uh, it would be reasonable to believe that, where do we have this? Oh, there's a max here, by the way, 2309. Was that what we? Oh, yeah, of course, that makes sense. This is returns the maximum of the two. Yes, of course. And then here we have the div. Exactly. So this there feels like this whole subtree here is kind of like somehow binding these functions to these names, and then they can somehow be reused uh, later. Um, so what's the what? How does that mechanism work then? Uh, how would that how would that system work? Because uh, we uh, uh, it's interesting. And then I assume that these lambda things define like our lambda expression so that we can like define a function. Oh, and then this is the name we give to it. So this is helper. So that like you have this tree structure like this, where you have like the name here, and then you have the so you bind the right hand side to the left hand side essentially here. It's like we have this whole tree here, which is a lambda expression which we bind to this name, and then we have the same thing here. So this is fold. Okay, and this is an or then maybe, but wait, did we have already have or as a no? Okay, that does make sense. We have mul and car. Okay, so okay, that's fine. We should be able to kind of make these into like sub-regions and like start grouping these according to their names, or so what's the best way of approaching this? Um, mm, so here's a hash thing. So, I mean, I could start doing some manual additions. Um, where do I do this? Here I print out the nodes so I can start doing um, so we can start um,
if we do something like this, already printed, we create a list, and then we get if we so we just move this thing into here. Okay, so we can uh, we can now start grouping these things together. So if we just manually kind of identify these kind of like roots of each function, and then we can build like a subgroup or a sub graph of this. There's a problem though, because we have some of these which are referred to in multiple places. Maybe that's fine. Maybe. Um, um, Here's the verify function, which is this whole subtree. So it's basically like hashing and comparing against these two constants. This is kind of readable, actually. You have a mod function in here. As long as you just get rid of. Can we create a transpiler that takes the graph and instead output some function code? Yeah, that's probably what we could do. It's just going to be, I'm just thinking like a good way to kind of like format it that doesn't, that actually is like useful. Uh, of course, you can just like collapse this whole thing into like one line basically of all like the function calls in kind of like a Lisp notation thing, but um, that's I'm not sure uh, how easy that will be to. I don't even think that if that actually will help. Uh, so hold. I'm gonna do. Let's add a small thing to the nodes. Um, yeah, it's going to be a long line with a lot of parentheses, which is not really going to be more readable than this. Where did I create the label thing? Here. Uh, so we can remove this thing. Um, we can probably do something like this, and then we do graph is node background color. Fill color is the name that we are looking for. Maybe not. Oh, maybe it shouldn't be the. Can I provide this as a hex value? Yeah, you should be able to do this. Low. Where is it? Why is this not working? Uh, is it just color? Okay, good enough, I guess. These are those function expression things. Oh yeah, and that was then should have been black as the default. Okay. So for example, here, let's see, helper. Up here, we're defining this helper function, I think, which is kind of like this area here. And then we're calling it here. Same with the fold, same with the lol.wtf function, which is also called here. But where is it actually defined? Here, this is the whole thing. Oh, okay. Yeah. Uh, uh, uh. At least I'm pretty sure we can say that these are constants. I mean, this is going to be a very minor change to the whole thing. Then we can just do its value, and then we mask out think this is how you would do it. Yeah, that seems to make sense. Okay. Um, so we have some constants here. And this actually is interesting because here we have like the specifically the constant zero, and this is kind of just like an empty node. Maybe we should just get rid of those and not display them at all. So uh, the value is actually 0. Let's just not print the node. If leave value 0, continue, and then of course we need to if node dot left dot oh, actually here no, here if node dot left dot value is not 0. So we just skip printing them. Yeah, this looks kind of fine. Guess not terrible. Um, Here we have all the function definitions again. Here we have the OR function. So then maybe we should just trust that this is like an OR. And here we can trust that this whole thing is like a mod function and that this is an add function. So there's just going to be a little bit of the code that we need to care about. It's going to be this like verify, this helper, and the lol_wtf function. And it's going to be, so we have like this whole subtree here, which has like, what's going on here? It goes down. Uh, uh, so here's some kind of recursive function, right? Because we define this function and then it's calling itself here, which makes, I mean, that would make sense. Doesn't seem, just a bunch of if statements. What was the if was like handled in a special way? Uh, which is interesting. We have bold. This is, which is this? Massage. Here we have some, we take them. So maybe this is just this constant, which is 31. Maximum of, so I'm trying to kind of like interpret this. Like we take the maximum of a, maybe we should like just try to translate this whole thing up into, like if we take the maximum of a and this value, and then you subtract this value. Yeah, that would make sense. And then you multiply it by this, and then you take modulo this. Yeah, that would make sense. That's like this whole massage thing. So basically, we would have like, well, it takes some kind of argument. I'm not really sure. Is it just like a single value, like some argument A, then I guess? And then this would return a maximum of A and 5F minus that multiplied by D and then mod 1F. That definitely would make sense. So that would be the whole massage thing. And then the helper here, what is this doing? We have some variable B, and we're adding, what are we adding together? We're adding together the result of massaging B and multiplying A with 1F. Could that be, could this be like, what did I say? We massage B and we add A. No, wait, and then maybe. And where would the helper be called? So we do we also have like a fold function, which is, let's just assume that this is a regular fold thing and not worry about it. Where is the or? Okay, where is the not? That's fine. Hash. So the hash function would fold with the helper starting with we have some argument. The hash, I mean, it makes sense that the hash is basically performing a fold over the input Maybe the helper is just, what did we say the helper was? Yeah, okay. So that would be the kind of function in the, but wait, what's the, we should only have one function. Okay, let's look at this thing instead. Where is this defined? Up here. Here we have some argument A, and if uh, hmm. I mean, these seems to be just be a bunch of list operations, like the cons and cadder and some variable A. So maybe the whole thing is just like basically doing this operation. Maybe we don't need to care about this too much. Then what would the verify thing do? The verify would have some argument A, and then I don't know exactly how the if works, but uh, or this is probably just the two halves of the hash. We're hashing A. Uh, we're subtracting this value from the result of the hash, which is just basically the same thing as comparisons. Uh, and then we're also doing this on this side. Maybe we could try to see if we just take a bit of a leap of faith here and try to implement this. By the way, 5f, is that's like a lowercase uh, x. 5f is, yeah, that's roughly where that's the underscore. So probably I mean, that makes sense. Like all the inputs then would be like underscores and lowercase characters and possibly what was it? We had there this range because it's going to be this mod. Yeah, probably that ASCII range. But is it just a addition? Because mm, all right, we keep it's a fold. So this would be right. So we're taking starting value, we run it through this function, and then we add the next element in the list and so on. And this is the fold, and that gives us the hash. Okay, so this we should be able to implement this. Can I copy these values, please? Here in the thing here. Yeah, I'm gonna have to hurry up if I want to make the, what was it, roughly 2.5 hour thing. Um, okay. Um, maybe this is just like two halves of it. I don't know. how would we reverse this? We would kind of like divide off and then subtract. Okay, this is like const 1 and const 2. So the idea is that we kind of like should unfold this by shaving off. I get an extra hour for not going dynamic analysis. Thank you very much, Lars. So the idea here, let's try to do this forward initially, just to get a feel for um, uh, plus a, yeah, okay. Hash of a result is, let's start at 0 for each byte in a. We do so if I have understood this correctly, we take the existing state, mm, this doesn't feel really good though, because no, this is always going to be a value between, it must be the other way around. Like, but we cannot just be summing. That will not give a unique value. It doesn't make sense. Let's have a look again. So the fold hash here, the hash function works by, we have this lambda, we do a fold, we have a helper, and we have the lol WTF. I don't really understand why we have two, like usually a fold you have like, oh, maybe this is, okay, so we take the result. Hmm. Yeah, I mean, usually a fold, like you take a starting value, you take like a sequence and you take a function and you combine, like you feed one element each from the sequence into the function, and the starting value kind of like is like a running sum or something. Um, the massage thing is always going to be a, and then you have the helper, which, okay, maybe that's, I probably need to be careful here about like which variables they use to like bind to different things. We add. Oh no, look, I forgot here. There's a multiplication as well. Oh yeah, okay, then it makes sense. So we multiply A with this, and then we add it to the massage. Massage of B. This would make more sense. So you take the value, you make sure that like it's in the correct ASCII range, you multiply it, you take a modulo, and then you add it to the like you multiply the current result with this, and you add this, and then you run this whole thing. Now we get something that's kind of like reasonable. Let's see. Oh, we're supposed to be lowercase. Yeah. Okay. Okay. I mean, we're getting something. And in that case, we should be able to just do, I mean, so for every, we need to invert this, but these are like, these values are going to be relatively prime, right? Like 31 is a prime number, and this is going to be 14. So, um, then you can do like result is this list, and we do while c is larger than 0. We do so we kind of like slice off this chunk, and then we need to uh, divide like take like the inverse uh, this. So have this in like can I do is this all right, you can do that. So uh, we should be able to do that. We should just take this left thing, and then we invert this modulo 31, and then we need to add the 5f thing, and then return this result. Uh, see if this gives us anything reasonable. Uh, oh, remainder. That's the wrong mathematical operation. Or is it? Actually, I'm really sorry, Lars. This is I'm committing crimes here. Um, uh, mm, oh, look at that! Uh, yes. This looks very good. Uh, am I just like? No, I was not off by one because like the format was correct. This is just some. Uh, uh, hmm. We're almost there. Was there like a known format for the flags? Was this given to the players? This is. I'm doing something very slightly wrong. I mean, you can clearly see here that like the normal flags format. What was that? Like MNS? No. Uh, or is it just flag? Or yeah. Uh, oh, midnight. Oh, look. Okay, right. Here it is. Yes. Okay. Mm, ah. Ah. And then I can switch this to salt. I think that was almost exactly 2.5 hours. Wow, nice challenge. Okay, so um, small recap. We found this. So we have a main function. The main function takes that. Oh, by the way, we should just. of course, we need to do and verify this. Win. Yeah, I tested it in the checker and it worked. So we have this main function. It takes in an argument. It converts this string into this like a list, like you would expect in something like Lisp or something. Let's see. Does the notes file make sense? Diff muffed by kind of. Oh, is it what it sounds like if you are lisping when you're talking? So we convert the string into this tree structure. Then you pass it into this function that which also takes this like other structure as an argument. And then you have this recursive thing which operates on the kind of like this, our input and this tree structure, and it does a bunch of things. So if we look at this tree structure, if we like parse this and write this out as an image, we get this. So this represents like the program tree of this. So this is, I don't know if this is like straight up Lisp and oh yeah, Lars, have you sorted out your microphone now so you can? We can get Lars on here to maybe give us some behind the scenes stuff. But essentially, this is kind of like some Lisp variant program. Do they have like an example? Can we have something big, something like this, which is essentially like a big tree structure? And then we can kind of figure out that first of all, we have these expressions, which binds like these function names to these like actual implementations. Like these are offsets in the program into these operations. And then you have this like whole pattern here. Like you have a name, and then you have a lambda thing here, and then this whole expression that comes below is like the implementation of the function called this name. And this way you can see that the verify function here is a function, and it uses these constants here, okay? And it also, let's see, where do we have that? It uses these hash function here and here. And the hash function itself is, where's the hash function? It's here in the middle somewhere, right? We have the fold. Hello? Massage, lol WTF, mod, add. Where did my hash function go? No, okay, this is the definition of the hash function. Cool. Yeah, Lars, like if you call me on Discord if you want to jump on and talk about it. But yeah, so this is the hash function, which does a fold using this helper function and the lol WTF function. And the lol WTF function is up here. And here I kind of just made a guess. Like there's a bunch of ifs and a bunch of cons and CDR. So a bunch of list operations. So I'm just assuming that it's taking like one element at a time in the list because it's not really doing anything else of interest. So that was kind of just a guess. And then the helper function here does an addition between two operands here. So you have like the left-hand side of the addition here,
which is the multiplication of the variable a with this constant. And the right-hand side of the addition is the calling massage with this argument b. So, and then massage is this function here, which does this. You can see this tree. You basically read it from the other end. You take the maximum of this constant and no, sorry. You take the maximum of this constant and the a variable, and then you subtract this constant from the result of that, and then you multiply the result of that with this, and then you take the modulo of that modulo this constant. So you kind of like read this backwards, upwards. So then I just like, made some educated guesses and like, what's the, let's see here if I can join. Hello, Lars.
Hello, do you hear me?
Yes, I think so. Do the viewers also hear you? I
Does
think
the
they should.
audience as well? Yeah, let's check.
I'm just gonna lower your volume a bit, but otherwise that's fine. I'm also
I
gonna
don't
add
see anything right now. I closed down the YouTube stuff.
Yes, I'm gonna add some noise reduction on you. Yeah, they can hear you. Great.
Perfect.
Nice challenge.
So, do you want to hear my thoughts, design thoughts behind it?
Yes. First of all, is this like some specific dialect of something, or is kind of like something you made up, inspired by some like Lisp or
No,
similar?
it is Lisp.
Yeah.
Yeah, it is Lisp, but I wrote my own sort of program for it. There are actually projects online where you can write your own Lisp. So it's pretty easy to implement Lisp. It's only like a few hundred lines of C. In my case, I think it was 300, but you can do it in 100. So the thing you might notice with the top bits of the pointers or anything, those are called tags.
Yep.
So I used 0 for normal pointers and 0, 1 for integers, which you called constants, and 1,
Yep.
0 for symbols.
Okay, nice. And then,
do you want to have a parser script, by the way, for extracting it as Lisp code?
yeah, do you have that? I want to see what it,
I have it.
looks like.
So here we go. Here we have some ugly. I pasted here in the.
Yeah. Okay, let me copy this and then copy this into here, and it already imports it. Okay, let's try to run this. Oh, nice. Yeah.
Can you share a screen with me, by the way, or is
yes,
that
I can.
because
I can
don't see
share.
anything now.
I can share the screen. You should be able to see the VM now.
Yeah, I do. Yeah, so there you can see the functions as well. And this lol, what the fuck? You didn't really figure it out, but you sort of managed anyway.
Yeah, is that the like that? That's like the every other or something thing, or?
Yes.
Yeah. Okay.
It is. So what you can see there is that in the verify function, you first do a hash of a, and then you do a hash of cadre a.
Okay, and then it skips the lol WTF skips every other.
In the hash function, lol WTF is taking every other.
Right, and since you
character.
start at offset 0 and offset 1, and then you get this thing. Okay, yep, that makes sense.
Yeah, so it's pretty condensed Lisp code. This code here is much more clear if you add some new lines into it, because then it's.
Yeah. I mean, if you start adding these things, yeah, I don't think it would have been faster for me to try to like build a script like this. I think just making the
Something that I
graph like
reacted on
this.
also
Yeah.
is that your graph here does not show the difference between right and left nodes, and those have a semantic difference in Lisp.
Yes, that's true.
But you managed anyway.
Yeah, I just hoped I kind of just made educated guesses from the values and like what's the reasonable thing a program would do.
Do you want to know about some other names? It was one variable that you called tree with your reversed.
Yes, this thing, the kind of global, like the entry
Do you want
point or
to know
whatever.
what? Yeah, no, it is actually the environment.
Okay.
So it is a linked list, and if you go into this transform one, which is actually the eval function.
Yep, I mean that makes sense.
Yeah, so it's evaluating a Lisp expression given an environment.
Yep.
So now if you go here, it's somewhere you should see is if something is a symbol, this thing that we are evaluating. If it's a pure symbol, then it's going into this so one of the other transform functions. Yeah, transform 2. Now when you know that tree is the environment, can you guess what this function is doing?
I guess so. This, I guess, then would be adding stuff to the environment if we have
No.
or reading from fetching it from the environment.
Yes, it's
Yeah.
lookup. So it's
Yeah.
looking up a symbol from the environment and getting the result.
Okay. Right. So we are, but okay. So we are never modifying. Where's the output here? So how does there must be a way to like modify the environment as well then, right? Is that the other one?
Yes, and that is what is
Yes.
done in the lambda function down here. So what you're doing, one of the concepts in Lisp is that everything is sort of immutable.
Yeah.
So what you're doing is that you are consing new environment, like new variables on top.
Yeah.
So this is how the recursive calls are handled, because the variables are overloaded with new ones.
Yeah. Okay, that makes sense.
And there is no sort of garbage collection at all, because it's supposed to just run once, and there are no frees at all in this program. We're only doing mallocs. Kind of ugly. But what we're doing here is that N4 here in the at line 39 and 38.
Yep.
N4 is this lambda expression. If you go back and look how this is defined in the output that you got from the parsing script, you can see that here we define. If you look at the first one here, we define or.
Yep.
When you look up, you will get this expression as a result, and then we have a lambda expression, and then we have the two variables. So it's having two arguments, b and a.
Yep.
And then yeah, yeah, that's I wanted to implement as few functions as possible with native code.
Yep.
So
yeah, that makes sense.
You can see that both I only implemented sub and NAND.
Yeah.
So you can look at the definition of AND a bit further down there.
What is it you have?
So you have
Here are these.
Yeah, those are native code.
The native code, and then you have the or and the not. You have the add and the mod.
Can you see how add is implemented?
So yeah, okay. I mean, this is like just subtracting a negative value, basically. Like inverting one operand and then and then subtracting, and then the mod divide multiplies. Oh yeah, okay. So we do like a floor division and then multiply back and then subtract that to get the remainder.
Yes.
Okay, that all makes sense. And then, yeah, so like the hash is just, so why here, what was the purpose of this helper? Let's see, the helper itself does what I said, but why, let's see, fold
takes 3 values here. It takes a function, and it takes that it will reduce with, and it will take
the start value.
The start value, and then the list. And the list here is every other character of the input string. So the helper function here, what it is doing, it's doing this multiply that by 31 of one part, and then doing this massage stuff on the rest.
Exactly, but why? Okay, I guess. Could you have moved? You could have moved this to the call, right? Or like instead of doing hash of a, you could have, that would have been the same thing, right? To have just a here and then the lol WTF of a here.
Yes.
Yeah.
But I wanted to. Yeah, but then I would have to duplicate it before both the hash calls, and I wanted.
Yes, that's true. Yep.
So I actually wrote an optimizing compiler to make the data structures for this. But you might have noticed that this tree that you were looking at, it wasn't really a tree; it was a directed acyclic graph.
Yeah, exactly. So that's what I realized, that it was. I mean, because it was mostly the constants and the variable names that was being reused.
Yes.
And we still see
this. This is also, by the way,
here, like down like this.
This is, by the way, why the arguments to the functions are in the opposite order, and that is to optimize the linking here, because then I can use CBA or BA and A, and they will be the same all the time.
Okay. Yep.
So they will be sharing the same internal data structure there.
Yep. Cool. Let's see. I can see if I can see my exact time here. So 9,000 seconds.
The thought I have with this challenge was to make something that was not very difficult to reverse assembly code wise, but actually to be difficult to like the challenge would be data structures. So putting that focus on the reversing effort.
151, so just over 2.5 hours was my final time.
Yeah, but you also had this extra. I think what I heard most teams during the actual CTF solved it was they put a breakpoint in the sub function and then did the analysis there from there.
Right, because since the hash function works the way it does, you can basically do this character by character, right?
Yes, it is linear. So
you can just put a breakpoint at the sub thing and then try character by character until you get like a partial match and then continue.
Yes. And it was a sort of intention. It wasn't supposed to be super difficult flare-on level, but
No, I mean, it was actually more difficult than expected. Although, I mean, you gave me the limitation of not doing dynamic analysis. So yeah.
Yeah, it wasn't. That was sort of self-inflicted limitation, but I kind of liked it that you actually took the time and went through and wrote the parser for the data structure. That's nice.
Yep. Cool. I think that's basically it
when
for
I
now.
wrote this, I
Or
had
yeah.
sort of you in mind. Yeah, I had you in mind from last like DEF CON when you were.
Oh yeah,
when we
yes, I think was it Skyto mentioned this in the chat as well with the data flow decompiler thing. That was certainly an experience. Okay, cool. I don't know, any other closing thoughts, or should we wrap the stream up?
Do you have any questions to me for the chat or in the chat?
No, I think you answered most of it with this explanation. It's a good challenge. It reminds me of the last time you gave me a challenge, which I did try it on stream, which was also like a virtual machine, the stack thing.
Oh yeah. Yeah, there was a fourth sort of inspired challenge.
Yeah.
Yeah, but I wouldn't really call this a virtual machine though, because it's sort of an interpreter or an eval function.
Yeah, but I mean, now you're going. Yeah, but I mean, it is a virtual machine in the broad sense. But yeah,
in a broad sense, I can agree, sort of. But
yeah. Anyway, thanks for the challenge. I hope. Well, do we have any questions, comments from the chat before we wrap this up? Actually, let's see if anyone has anything. Otherwise, we will be closing this up. Been streaming for almost 3 hours. I thought this was going to be like a quick, short stream, but yeah, it was not 6 hours at least.
Yeah, I'm sorry. I hope you enjoyed anyway.
No, it was fun. It was fun. It was great. Cool. Yeah, thanks everyone for watching. And we'll see when I stream. Yeah, so question, how often do I do this? Very irregularly. So we'll see. But if people enjoy these things, like I might do it a little bit more often than I've had a lot to do this year. But now hopefully I will have like the rest of the year will be pretty chill, I think. So maybe we can do some more of this. Yeah, we'll see. I don't have a regular schedule, basically. Follow me on Twitter. I post before I stream. Yeah, thanks for watching. Goodbye.